Welcome. In this video we'll understand how a recurrent neural network, or RNN, remembers previous words in a sentence. We'll use a simple example, I love movies, and walk through forward propagation step by step. Before any neural network can understand text, words must be converted into numbers. This is called one-hot encoding. Our vocabulary has 3 words: I, love, and movies. Each word gets its own vector. I becomes 1, 0, 0. Love becomes 0, 1, 0. And movies becomes 0, 0, 1. Only one position is hot, meaning set to 1, and the rest are 0. Each one-hot vector becomes an input feature vector. x1 represents the word I, x2 represents love, and x3 represents movies. These 3 vectors will be fed into our RNN one at a time, in order. Why do we even need an RNN? A normal ANN, artificial neural network, treats every word independently. It has no memory of what came before. But language depends on order and context. Movies means something different after I love versus on its own. RNN solves this by remembering previous words through a self loop. Let's look at the RNN recurrent cell, just like in our diagram. X is the input at the current time step. H is the hidden state. Y is the output. WXH are the input to hidden weights, Y are the hidden to output weights, and F is the activation function, tanh. The small square shows the recurrent self-loop connection. Tap on any term to see what it means. This same cell repeats at every time step. That's called unfolding the RNN over time. At time t-1, t, and t+1, the network takes the current input, combines it with the previous hidden state using WXH, applies the tanh activation F, and produces the next hidden state, which then generates an output using Y. At each time step, current input plus previous hidden state gives a new hidden state. The word recurrent simply means repeating loop. In an RNN, the same set of weights are applied again and again at every time step. The hidden state feeds information back into itself, which is what gives the network memory. Now let's convert our sentence into vectors. I becomes x1, love becomes x2, and movies becomes x3. Each word is now represented as a numeric vector that the network can process. Let's process the first word, x1. Say we have 5 input features and 3 hidden neurons. That means we need 5 multiplied by 3, which is 15 weights connecting input to hidden layer. The formula is, h1 equals tanh of wx.x1 plus b. Wx is the weight matrix, and b is the bias. Since we have 3 hidden neurons, we get 3 output values. Together these 3 numbers form the hidden state, h1. This hidden state stores compressed information about the word I. Here's the key idea, the self-loop. The hidden state h1 doesn't disappear, it gets fed back into the network for the next time step. Look at the diagram on the right, that small square next to h shows exactly this self-loop connection. This is exactly how the RNN remembers previous information as it moves through the sentence. Now we process the second word, love. The formula becomes, h2 equals tanh of wx.x2, plus wh.h1, plus b. Notice the new term, wh.h1, this brings in memory from the previous step. So h2 now contains information from both I and love. Next we process the third word, movies. h3 equals tanh of wx.x3, plus wh.h2, plus b. Now h3 contains accumulated information from all 3 words, I, love, and movies. Once we reach the final hidden state h3, it gets passed through an output layer to generate the prediction, y hat. This prediction is based on everything the network has seen across the whole sentence. Let's quickly trace the whole journey. X1 flows into H1. H1 flows into H2. H2 flows into H3. And H3 finally produces our prediction, Y hat. Information keeps flowing forward in time, and at every step it gets stored inside the hidden state. To check how good our prediction is, we calculate the loss. We use cross-entropy loss, calculated as negative of y log y hat plus 1 minus y log of 1 minus y hat. Here, y equals 1 means the positive class, and y equals 0 means the negative class. This compares our predicted value y hat with the actual value y. The smaller the loss, the better the prediction. Let's put it all together. Our sentence, I love movies, gets converted using one hot encoding into X1, X2, X3. The unfolded RNN computes H1, then H2, then H3. The self loop helps the RNN remember past information at every step. The final hidden state produces the output, Y hat. We then calculate the loss and compare it with the actual label. This entire chain is called forward propagation in an RNN. Here's the full visual map of everything we just covered, all on one page. Tap the image to zoom in and look closer at any part of it. Quiz time. What does the term recurrent mean in RNN? Next question. In one hot encoding, how many positions are set to 1 in each vector? Next question. What information does the hidden state H2 contain? Next question. What is the formula for the third hidden state, H3? Last question. Which loss function compares the actual output with the predicted output in this example? One more. What is the difference between WXH and Y in an RNN cell? Let's quickly summarize using the full picture. Words are converted into numbers using one hot encoding. RNN remembers context using a hidden state and a self loop. At every time step, the hidden state combines the current word with memory from the previous step. The final hidden state generates a prediction, and cross-entropy loss tells us how accurate that prediction is. Tap any number on the picture to revisit that part. That's it for this video. Thank you so much for watching. A heartfelt thanks to Ajay Sir for his guidance, and to my AI friends, Claudi and Smarty, for their support. See you in